Okay, so we are starting Chapter 2, Lesson 5 today, called Special Functions. This is for IM 3, mixing up my IM classes. So we're going to talk about definitely some special functions in this section. So a function that is written using two or more expressions is called a piecewise defined function. On a graph, a dot indicates that a point that is included, and a circle indicates that a point that is it is not included. So it's kind of the same idea as we've done before. Closed dot means it's included. Open dot means it's not included. It's kind of a starting point. A piecewise linear function contains a single expression. The step function consists of line segments. So here's a step function down here. We can see it. This is a piecewise defined function. So a piecewise defined function is kind of where we have more than one expression or function, and they kind of have limits. That's the idea. So it pieces itself together. So piecewise, hopefully that kind of makes sense why we call it that. So we also have the greatest integer function, which is it looks like a step. So it's like we also call it the step function because it literally looks like a step. The symbol f of x equals, and we have these funny little brackets in x, it means the greatest integer less than or equal to x. So that's what it means when we have these funny little brackets here. Kind of like the double brackets, I guess is what you'd call them. So for example, the greatest integer less than or equal to 3.25 is 3. So remember, it's less than or equal to the greatest integer. So we kind of just rounded down to the greatest integer, which would be 3. So that's just what these symbols mean. So here's an example of a piecewise, and if I scooch down, you actually see the equations here that help us make a little bit more sense of this. So we're given two functions, and when it looks like this, it's just two functions written for the same thing. So f of x equals x minus 2 if x is less than negative 1. So in this case, this is what the function equals. So we literally have this equation just like we would before, or this function. So we can go through and solve this. Remember, it's the same idea as y equals x minus 2, if that helps you picture it. So I can look at this as slope-intercept, and I can go, well, my slope is negative 2, and let's see, negative 2, which would be right here. And my y-intercept, I'm just saying all kinds of the wrong words right now. My y-intercept is negative 2, that's my starting point, and my slope is 1 over 1. So, and I can do that backwards so that I can kind of go down where I want to see this graph. But you could go up if you wanted to, but since it needs to be less than negative 1, I kind of want to go this direction, because negative 1 is right here. So I'm actually going to show you, that's my limit. That's what I want it to be below, is this line here. And I'm putting a dotted line just so we can kind of, that's a really horrible dotted line. Actually, I'm going to grab my line tool real quick. So it's a nice clean line. So grab my line tool. So there, that's my limit line. I want it to be less than that point. We'll turn that off. So for this first one, I want it to be less than. I want it to be the left side of that line. So I'm going to go down 1, left 1, because I can go negative, negative. Remember, two negatives make a positive, so I can kind of go the opposite. Down 1, left 1, down 1, left 1, down 1, left 1, and I would have this line here. But I wouldn't include this area, because that's not less than negative 1. That's to the right of it. So I ignore that area. So I could graph it real quick, but then I'd need to erase it. I'd need to fix that so that it wasn't included. Okay? That's just kind of a way we can graph it. And if I go back too far, I think I'm going to get rid of my red line here. Oh, it's going to get rid of all this other stuff. I don't want to do that. Okay, so ignore that dot, kind of like it wasn't there. I shouldn't have put it there before all of this stuff, because now I can't just simply go back. And if I erase, it actually erases the entire graphic. So the next one, and I'll do this one, and let's see. We'll do it in pink. Why not? I haven't used pink yet. So it's kind of a pink-purple color. So this is the situation if it's greater than or equal to -1. So if you notice, this was less than, it's an open dot. This is greater than or equal to, it's a closed dot. But I can still do this the same way. F of x equals x plus 3, which if I like to picture it this way, here's my slope-intercept form. So I'm going to go up to 3. There's 3, that's my y-intercept. And then if I go up 1 over 1, that way I can connect my line. And I just need to make sure that it doesn't go past this one. It needs to be greater than that line. Okay, so that's all piecewise means, is we're just piecing it together. Greatest step integer. So this is the function of x, or f of x, is the greatest integer less than or equal to x. So I would plug in a number, and it would be greater than. So if I plugged in 0, it would be 0. And I'd step over 1. And then if I plugged in 1, it would be 1. So it's just one step over. That's all it is on all of these. So it's just a cute little step here, and it's always closed, open, closed, open, closed, open. And that keeps it a function, because remember, if I draw my vertical line here, I'm crossing over 2, but the open dot means it's not included. So it actually passes my vertical line test. All right, so let's go to the next page here. I'm going to flip back to blue because it's a little nicer to write with. Move this guy up. I don't think there's anything above here. No, okay. All right, so we're going to graph this, the function, identify the domain and the range for this, I think for both of them actually. All right, so for the first one, what we want to do is just separate it like I did for that other one. We just want to break it apart into its pieces real quick so that we can kind of see the different pieces. So really quick, I'm going to use red, and I'm going to draw some limit lines on here. So this is if x is less than or equal to -4. So I'm going to go -4, 1, 2, 3, 4, and I'm going to draw a limit line here just so we have it. You're not going to do this on Alex. I'm just doing this as a visual so you can see this is one of my limits. And then between -4 and 2, we have this middle function. And if it's greater than 2, then we have this third function here. So these are my two limits. And depending on which one we're doing, whoops, I have to turn off the line tool. Forgot to click on it. Depending on which one we're doing here, it has a different limit. So let's do this first one. So f of x equals -3. So this is just a point. Y equals -3, if we can look at it that way. This is just quite literally a number that we would plug in. And we would just put a point on -3. Let's see, 1, 2, 3, sorry, 1, 2, oh, what am I doing? -3, 1, 2, 3. So I would actually have a vertical line going across like this, back and forth, because y equals -3. So this is y equals -3. It's a horizontal line. But remember, it needs to be less than or equal to -4. So I wouldn't draw it all the way across. This is my starting point, and it needs to be less than or equal to that point. So I would go over. And then, for the next one, we have, and I'll do it a different color here, we'll go back to pink. We have f of x equals x. And this has to be, uh-oh, what happened to my other red line? I didn't mean to undo that. I like my little limit lines here. Sorry, I didn't realize I clicked undo on that. I just noticed it. So now we can plug in numbers. If I plug in 1, forgot to switch back to pink. If I plug in 1, I get 1. If I plug in 2, I get 2. If I plug in 3, I get 3, because it is equal to itself. So y is equal to x in this case. So this is going to be a nice diagonal line. So if I go like 1 to 1, 2 to 2, like that, now I have a diagonal line I can see. So if I plugged in 0, I'd get 0. If I plugged in -1, I'd get -1. So I can kind of do this dot feature here like this. Keep in mind it says less than 4 and less than 2. So it's going to be open dots on these pieces. So I'm going to have an open dot. Actually, I want to kind of go down here because I want to go all the way to the 4 here. It's a really big open dot. It's going to be open here. It's going to go all the way up here, and it's going to be an open dot on this one. Okay, and I would connect this line. This is connected. But doesn't break the rule. This is actually a vertical line right here, this red one, but it's open and closed, so that doesn't break the function rule. All right, the last one, let's switch, use, I guess, yellow. F of x equals -x plus 6. So if I plug in, let's go with 0, I have 0 plus 6, so I get 6. Sorry, I don't want to say equals. I'm just writing, these are my coordinates. I'm just writing them kind of funny. So if I plug in 1, -1 plus 6, I get 5. If I plug in 2, -2 plus 6, I get 4. So this is definitely enough. I really only need 2 points to graph the line. But we want to make sure it needs to be greater than this line. So if I have 0, I would go up to 6. Well, that's in between. I don't want that point. If I go over 1, I go up to 5. I'm still not greater than. If I go over to 2, then I go 1, 2, 3, 4. I'm on the line, and that's fine because it's greater than or equal to. But I do need one more. So let's plug in 3. And let's see, -3 plus 6, I get 3 here. So I have 1, 2, 3, 1, 2, 3. So this is going down, definitely. If I plugged in 4, I would get 2. So I can see, I can go 1, 2, 3, 1, 2, 3, 4, and 1, 2. I can see that it's a nice kind of straight line there, and I can even grab my line tool just so that it's a nice straight line going down. Boop, 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 boop. Turn off my line tool. Turn it off. And then I would have an arrow going down like this. So this is what this piecewise function looks like. I know it's a little colorful, but I wanted to be, show you kind of the different pieces here. So there's 3 functions. That's what each one of these lines mean. There's 3 different functions. Okay, but none of them really intersect with each other. They kind of start and stop at the same points, but one should be open and one should be closed when this happens. And then again, you're not going to put the red lines here. This is just the limit lines. It's showing me where to begin and where to end, for each of the functions. So I like putting them there just to kind of help visualize it, I guess. So when we want to do domain and range, we just want to identify what are the limits here. So if I'm thinking of domain, I'll actually switch my color up here for domain. So domain, which is left and right, I want to know how far to the left and the right I can go. Well, this is going to go on forever to -infinity. And we're also going to go on forever, it looks like, down, but not as fast as this one. But we are going to go to +infinity as well. So we're just identifying, is there any limits? So when there's no limits like this, it's going to go on for infinity in both directions. We just say the domain is all real numbers. Okay? And the range, remember that's up and down. Do we have any limits here? Well, this would definitely be a limit because we're not going down any farther. So we identify the point at which we no longer go down or we no longer go up. This is actually going to go down more. So this, even though this stops here, this is going to continue to go down forever. So the range isn't really limited down, but we are limited to this point here. There's nothing above this point. So we would say the range is less than -3. So we actually would write it out with this f of x. So we put it in notation, and we would put f of x is less than positive, that's 1, 2, 3, right? 1, 2, 3, 1, 2, 3, 4. I can count. Less than 4. And really that's all you'd need to end it with, because we don't need to identify the infinity. It's just going to be less than 4 is our range. Or I would say less than or equal to. Sorry, I forgot the equal to since it's a closed dot. So that's our range. It's less than or equal to 4. All right, let's go ahead and look at our greatest integer function here. So when we were looking at the greatest integer of x on this other page, it started at 0, went over 1, up 1. It just kept going over 1, up 1, over 1, up 1, but it started at 0. So now when we have it x minus 5, the idea is that we're actually going to start at 5. So that's kind of an easy way to understand that. And with this one, if I actually plug in some numbers here, oops, I don't know why I changed h to f. It's h of x equals, if I have, and I'm not really great at drawing this, x minus 5, and basically I'm going to plug in some numbers here. So if I plugged in 0, I'm not going to get 0, but if I plug in 0, 0 minus 5 is 5. So this would be 0 and then 1. Oh, sorry, -5. I was going to say, wait, that's the wrong part of the graph. Ha ha ha. -5. So 1, 2, 3, 4, 5. So there we go. We're starting down at 5. And then I'm going to go over 1 with an open dot. And now I can just keep stepping it over. I don't necessarily need to keep calculating it. I can if I want to. Remember, these are all open. I know that's kind of horrible looking, but they're all open. And so it would keep going up and down forever from that point. And I can even test it. If I put in 1 minus 5, I have -4. And if I look at this, if I go over 1, then I go 1, 2, 3, 1, 2, 3, 4. I can count there. So same thing if I plug in 2, I'd end up with -3. So I can track this across as I plug these numbers in. So when we're thinking about the domain and range, again, same idea as this domain and range. We just want to see what are we limited to in these cases. So usually, let me see, I wanted to make sure I'm explaining. For the domain and the range, there really isn't a limit here. I'm going to go down forever. I'm going to go up forever with this step function. So it's just the greatest integer. If I start plugging in decimals, that's where the greatest integer idea comes from. So I can plug in 0.1 and I would subtract 5 from it and I'd end up with a decimal and I would go with the greatest integer. So that's what these little symbols mean, right? That's kind of the big deal there, is that you go to the greatest integer of what you receive in the parentheses here. But I would keep going on and on forever, up and down, left and right. So it would really be the same answer that we did here, where the domain is all real numbers and the range is going to also be all real numbers. There isn't really going to be a limit there. So except for integers, it does need to be integers. So I actually need to amend my statement there. It's not going to be decimals. So it's going to be all integers. Not real numbers. I should amend that a little bit. All right, so let's go ahead and go to the next one. We're going to look at absolute value function, and that contains an algebraic expression within absolute value symbols. So if we look at this one, and I know it's a little blurry here, but we have f of x equals the absolute value of x. So if I plug in 1, I'm going to get 1 because the absolute value of 1 is 1. If I plug in -1, the absolute value of -1 is 1. If I plug in 2, I will get 2. If I plug in -2, I will also get 2 because the absolute value. So now if we look at this graph, we can actually see if I go 1, 1, 2, 2. So I did the positives. Now if I go -1, I have to go +1. Because remember, -1 turned into +1 because of the absolute value. -2 turns into +2. So I can see this kind of V pattern happening, and I can connect them. So let's go ahead and take a look at this next one. And they do give you some more definitions here. So it's a V shape. It's all real numbers for the domain, because in this case it's going to go on and on forever to the left, on and on forever to the right. The range is going to be all non-negative real numbers because it starts at 0, so it doesn't go below 0. The x-intercepts in this case would be 0 because that's the only place it touches the x-axis. And it's not defined for anything below 0 because it's an absolute value. So it shouldn't be below 0 in this case for f of x. All right, so let's go ahead and try this guy out here. Graph each function, identify the domain and the range. So let's go ahead and graph it. I'm going to bring it over here just because I, for some reason, like to stack them. So if I plug in 0, in this case, 0 minus 2, I get -2. Absolute value of -2 is 2. If I plug in 1, I have 1 minus 2, which is -1. Absolute value is 1. If I plug in 2, then 2 minus 2 is 0. I don't have to worry about the absolute value 0 because 0 is just 0. There's no positive or negative there. If I plug in 3, then I have 3 minus 2 and I get 1. So now we can see that it's starting to go back up here. 4, so it doesn't match perfectly when it's x. X was matching nicely because it's 1 to 1, 1 to 1, or -1 to 1, 2 to 2, -2 to 2, like it was on that last one. When we start adding in this extra piece here, we're kind of translating over, and I'll show you what that means in just a second, but we're scooching over the graph just a little bit. So 4 minus 2 is 2. So now we can see the pattern happening here. So if I went -1, it should be 3. If I go 5, it should also be 3. So we should be able to see that pattern at this point. So let's go ahead and graph these. And on ALEKS, it's probably going to make you graph 5 of them. Usually that's what it does. And one of them needs to be the vertex, the bottom of the V. Okay. So that's going to be 2, 0. So that's the bottom of our graph here. And then we're going to have 0, 2, so that means 0, 1, 2. And we're going to have 1, 1. And that's going to go on and on and on and on forever up that way. And now we have 3, 1, and 4, 2. So that's going to go on and on and on forever that way. So here we have our graphed function, absolute value function. So the domain, just like it was here, is going to be all real numbers. It's going to go on and on forever to the left, on and on forever to the right. So the domain is all real numbers. So let's write that down. So domain is going to be all real numbers. Okay. The range, just like it was on this one, is going to be all non-negative real numbers. So non-negative real numbers. We can define other pieces of it too and say, you know, the intercept in this case is not 0, it's 2. So that's the translation. When I have in the absolute value, when I add or subtract, it's going to scooch it over to the right. If I added, it's going to scooch over to the left. So if I subtract, it's scooching it to the right. If I add, it's scooching it to the left. So it's kind of opposite of what you might think there. But it's just a translation. It just means I'm scooching it one way or the other. But it's actually still the same size graph. It didn't kind of squish in. It's the same width V, I guess, is what you could say. It just, all it did was scoot over. So this is the finished graph what they've asked us to do. Again, a lot of these will be drop downs, I believe, in ALEKS, but I will see you in the next section.